My talk today is Monoids on Steroids, a brief history of functional programming. I want to start with a quote. This is on Northern Library. While you're here on campus, you should visit Northern Library and actually see this quote. It says, "Who knows only his own generation remains always a child." That sounds a little stilted. I would say those who know only their own generation, but I won't quibble about that. But this is an injunction to not reinvent wheels that have already been invented and to do your due diligence to make sure you know about what your predecessors have done. There's the saying about standing on the shoulders of giants to see further, and you have to know that the giants are there and which giants are worth standing on their shoulders. So functional programming to me just means no mutation. That's all it means, at least to me. That's my definition. Maybe someday there will be mathematics that will have ways of doing mutation-free programming that won't involve functions or will have a different way of doing it. To my way of thinking, it's just about no mutation. And that's nice to have the thread safety. And I'll talk later about quarantining I/O. Closure has the idea of avoiding what they call promiscuous mutation. So I'm sad as a LISP guy. I'm an old timer. I went through the LISP days and worked for Symbolics, and I love LISP machines. I'm sorry that the world rejected LISP, and I think we'd be way ahead if the world hadn't rejected LISP. But despite that, we're getting caught up and making up for a lost time. The advent of Moore's Law kind of hit a wall. They can't keep making CPUs faster, but they can give us multiple cores if you can program them. And functional programming has the way to program them. And so this is really cool. So we're making up some progress here because functional programming is now the way to leverage those cores. And so we have a lot of advantages that we didn't have in the LISP machine days. That's all I want to say about that. So I'll kind of skip over this. I've given this talk in many venues, and it's different every time I give it, and I emphasize some slides and skip others. So we are making up for lost time. That's the main thing. The main goal is to try to achieve an algebra for an algebra-like way of manipulating computer code, and I think with Haskell and category theory we're getting there. So I want to start in 1847. George Boole invented Boolean Algebra. Can you imagine what it must have been like in 1847 to tell stakeholders that thought you were doing mental gymnastics that this was worth doing? He did this probably just because it was beautiful and interesting, and I'm glad he did. I can imagine stakeholders saying, "George, how is this going to make the horse and buggies run on time?" And then De Morgan's law, this is De Morgan and this is how we convert ands and ors and knots and push knots through and so forth. 1924, combinatory logic was invented by Moses Schoenfinkel. This guy here, he was a German Jew who left Hitler's Germany to skedaddle to Stalin's Soviet Union. I don't know if that was a big step up. I guess it was a bit. This is interesting because it reminds me of this idea of a RISC machine, a reduced instruction set where there's very few instructions, but you can composite these to get whatever you want. Using just SK and I, you can express everything that is computable, and you can derive some of these from the other ones, so they can say, well, we don't need SK and I, we can just get it down to just two of these. And then they said, well, can we get it down to just one, where you just have one combinator X, and if so, what would it look like? And the answer is yes. If you look in the Barendrecht, that yellow lambda calculus book, he goes into this and shows how this looks in lambda calculus. He is the one who invented currying, by the way. Most people say he invented it, but Curry got the credit for it, and Curry sounds better anyway, so I guess that's okay. In the 30s, lambda calculus was invented. When I was doing the slide deck, I didn't realize that lambda calculus came after combinatory logic. I would have thought it was the reverse, because when I do combinatory logic, I always convert it to lambda calculus and do it in lambda calculus, but that's just my way of thinking. But no, it turns out lambda calculus came later. 1936, Konrad Zuse, this guy was a Nazi, and he had a very pragmatic, or a very maybe evil way of looking at this. He just felt like you have to make a Faustian deal to practice your craft, and he had no druthers about doing that. This is quite remarkable, because remember the guy, Moses Schönfinkel, before, he was a German Jew, and here's a Nazi guy. But this is interesting. These players came from diverse places. He was the first one that had an electromechanical computer. 1937. Remember, in 1847, we had Boolean Algebra. Now in 1937, Claude Shannon, he took this admonition that we saw in Norland Library, know your past generations and what they did. He took that really to heart. He just noticed that he knew about George Boole and his work, and he said, hey, that's exactly what we need in this point in time to get rid of vacuum tubes and use Boolean algebra for logic circuits. That was pretty cool. That was his master's thesis, one heck of a master's thesis. 1942 category theory. This is very abstract set theory. I assume a lot of you went to the category stuff on the first day. It was fantastic. The nice thing about category theory is I like seeing computer languages being based on formal systems, because if they aren't based on formal systems, they're way too ad hoc and quirky, so you feel like a master of quirkology instead of a computer scientist. The interesting thing about category theory is if I were to show you conference proceedings from the 80s where they showed category theory stuff and the category theory from yesterday, you wouldn't see any difference. It looks the same. Category theory has been very stable for a very long time, whereas software has come and gone. We've seen languages come and go and software going in and out of vogue. So I think category theory is a great thing, and it will stay stable like that for a long, long time to come. 1958, this is the year I was born. I don't think that's a coincidence, but I'm biased. This is when LISP was invented based on untyped lambda calculus, and we had S expressions. I really like S expressions. A lot of people didn't because they thought there was too many parentheses. Haskell goes the opposite direction to try to avoid parentheses at any cost, using dollar signs everywhere possible to avoid them. But I like S expressions. A lot of LISP lives on in the G's of other things. And I think there will be things that LISP will be credited for and rediscovered in the future. We're seeing a little of that with Clojure, I think. But it has a good place for embedded languages. If you want to use an interpreter pattern, writing a LISP interpreter is a very simple MIT freshman level project. Very easy to do, and S expressions makes it really simple. So I really like LISP. 1970, object-oriented programming came out. I think that was a step backwards. I don't think everything is an object. I think everything is a value. If you try to implement functional programming in an OOP-centric world, functions become orphans. You have to have some phony, faked-up class to stick them in. Otherwise, they're orphaned. And so I'm not a big fan of object-oriented programming. I think that's all I want to say about that for now, although I think it's going out of vogue now because most languages like C# are heavily infiltrated with things like generics from functional programming, so there's no real pure object-oriented systems anymore. They're all diluted with a lot of functional programming, and I think you'll see that more and more in the future. Prolog, 1972. When I was going through school, I'm actually a CU Boulder alumnus, my alma mater, and I remember in the early days when Prolog came out and the Japanese were betting the farm on this. They thought this was going to be the way of the future, and I knew then that that would not be the case. But Prolog filled a very interesting niche because when you do type inference in Haskell and F# and so forth, that's essentially like a miniature Prolog engine in the background working out your types for you, and that's pretty cool. So it did find a place. 1975 Scheme came out, MIT's dialect of LISP, And these guys had a huge contribution to make in the idea of first-class citizenship. These guys were the ones that drummed into the world this idea of, if you can put integers into an array, you should also be able to stuff function definitions into arrays. Otherwise, functions aren't first class, right? And there's a lot to be said for this idea of first-class citizenship. Schema is strict. I wish LISP had been non-strict. I wish Scheme had been non-strict, but it is strict. There's probably good reasons why they wanted to be strict, because in those days, there's a lot of concern about using mutation, because the ways of non-mutation hadn't been solidified, so that's a good compromise, a pragmatic compromise. 1983, Symbolics came out with Lisp machines. Does anybody remember these? These cost about $40,000, somewhere around that neighborhood. They were very expensive. They had tagged architectures. This was the ultimate in dynamic programming. You could pass anything to anything. The types were resolved at runtime using a tagged architecture. The extra tags would recover the type information, and as long as the type information was okay right at the last split second, then it would let you do it. I think way up there you see the meteorite hitting the dinosaurs. Around the same time, Haskell was being born. Haskell would be born in '87. But the idea of type inference and type systems was starting to get debated more and more. And I think that was ultimately the end of the Lisp machines, although they probably did lots of things to do themselves in before that happened. But the idea of being able to work on stock hardware is hard to compete with when you have a very, very expensive custom architecture. 1987, Haskell was born. I was actually at the conference where they actually had the meeting. I believe it was in Portland, Oregon. And they decided, let's stop. At that time, there were all these different little languages popping up here and there, and they said, let's actually come up as a community with what we think is the best practices and one language that we're going to say this is what we think of as the best way to do functional programming, and that was Haskell. And I'm glad Haskell was lazy. Lambda calculus is lazy. There's a lot that you can do with laziness that you can't do in a strict system. Haskell was not really viable in the real world until monads came along, and hence the title of my talk. When you think about monads, they're really just embellished monoids, or monoids on steroids, and that was the missing puzzle piece to make functional programming a dream that could come true in the real world. Before the advent of monads, it wasn't really very viable. 1992, monads. Phil Wadler, I think he took them from, is it Mogi or Moji? I'm not sure how his name is pronounced. Came from category theory, but Phil Wadler's the one that said, this is what we need in Haskell. Let's do this in Haskell. 1998, XML came out. Lisp people were kind of jeering and saying, we've been doing this since the 60s. Where have you been all this time? Or whenever, yeah, about the 60s. But in a way that's true. S expressions are kind of like XML, but this is, if you think about it, this is a much more type-safe version of S expressions, because I can't use this closing tag to close off one of these or vice versa. So there's actually a little bit more type safety. It's a little more verbose, but you have a little bit more type safety. It's still not very type safe because you're coercing from strings a lot, but I really like XML a lot. 2005, F# was invented. F# is in the ML family of languages, invented by Don Syme. It's strict. ML is strict. And that's for good reason, because it's a hybrid language. It doesn't attempt to be pure. And if you're going to interoperate with the real world in mutation-based systems, having that pragmatic trade-off is, I think, a very good good idea. The object-oriented programming in F# I think is pretty elegant. It mixes functional programming and object-oriented programming in a very elegant and tasteful way. F# has computation expressions, which are a very flexible form of monads. They're not exactly the same as real Haskell monads. Sometimes I use Haskell when I get lost in F# because F# lets you cheat, and sometimes you want to do Haskell to really get clear on your thinking. FP, everything's a value, that's the way it should be. Composition is the best way to control complexity. I'm really a believer in that. Monoids are a nice way to quarantine things that don't fit into the normal functional paradigm very well, that are problematic. And the multiple cores, now that we have Moore's Law, we're seeing FP enjoying some acceptance that we didn't have in the LISP days. There's some talk about the impedance mismatch between object-oriented programming and databases, and from my point of view, with functional programming, the impedance mismatch basically goes away because functional programming is so synergistic with relational calculi and sets. And we've heard a lot about monads at this talk. I think that was the key piece that now is making functional programming a dream in the real world. It's interesting to see how equational Prolog is, and Haskell is very equational like that. Scheme is less so, it's much more like a Lisp. Type classes, I think, are a great innovation. I wish we had them in F#. I don't think that F# is ever going to get them. Discriminated unions are wonderful. When you think about it, C# does not have OR types. It only has AND types. And having OR types makes a huge difference in modeling a domain. This is a Haskell example. So I had a big hobby of plotting things. I like to see mathematical expressions plotted so I can see what they look like. And I started in the old days on an Apple II with a very basic stuff. And then at one time it was on a Macintosh and using a Mac scheme. And at one time it was on Symbolics LISP machines. Then I decided I want to build my own machine, and you can't build Macs, so I decided I'll build a Windows machine. And it's really cool to build your own machine and be able to run an interpreter that you wrote yourself. That's pretty cool. This is Bill Gosper. He's the one that invented these vector-based fractals. And Winston and Horn, they talk about these, and I thought, these are so cool, and you just keep using these rules, and you get these interesting plots that look like this. I wanted to have those in my fractal programming. This is a Mandelbrot Peano curve based on those vector fractals. So I wanted to have a plotting program where I had an embedded Lisp interpreter so the user could change the equation to be plotted. And I want to show you for, I'm going to take a little brief timeout here for actual code sample. This is from my fractal program. So I'm going to run that one you just saw, and I'm going to run the built-in one first. Where is it? Where's it? Was here just a second ago. I have too many of them here. Let's see. Oh, okay, this is the built-in one. This one is in pure F#. I'm going to press plot, and you can see it comes up pretty quick. Now I'm going to run it through my embedded Lisp interpreter that I wrote, and let's see how fast that one is. I'm going to press the button here. It's relatively quick compared to the built-in one, and yet this is running a lot of Lisp code in my embedded Lisp interpreter that is written in a very naive way. Let me show you all the Lisp code it's actually running to accomplish that. See all this Lisp code here, all the way down to here? So from the Lisp code starts, I'm having trouble scrolling here. It starts here and it goes all the way down to about here. It's running this Lisp code for every vector and even the ones you don't see, and yet it's doing amazingly fast, and it was just a very simple little interpreter I wrote, and that was kind of my dream to do this. So this is a very viable way of letting the user change equations at runtime without having to recompile your code. So getting back to where I was here. Oh, lost my place a bit here. Okay, so we're here. Here's some of my, I have a little Lisp pane where I can test my Lisp code. I give you the opportunity to tokenize it and see what it looks like, heapify it, just to make sure that you are convinced that it tokenized it and heapified it correctly. I also do L system fractals. I just think these are interesting. I like any kind of visualization. This is an equation I came up with when I was taking calculus. I wanted to see what inverse hyperbolic transcendentals look like, and I came up with this and played with it. If you keep plotting it, it will go on for infinity, and the hearts will just keep getting bigger. These are complex plane fractals. How am I doing on time? Oh, good. That's good. This is kind of interesting. The complex plane fractals, you can see these boundaries here. And these demarcate the real roots versus the imaginary roots. And by looking at this, you can say, oh, this has, I think it's 2 imaginary roots and 1 real root, I believe, where these boundaries are. And this is the critter here that I'll zoom in on so you can see a little more of that. Here's the critter zoomed in on. The interesting thing about these is you can zoom into infinite smallness and it keeps getting interesting fractal pictures. Okay, so some of my conclusions. I really like Haskell a lot. It's my favorite programming language. It's the most expressively powerful language. The downsides are it doesn't have the interop that F# does with the .NET framework, and that means a lot to me as a professional .NET programmer. F# is very nice. It has good interop, but it's impure. And sometimes because it is impure, you cheat, and you get lost because you cheat. I like WPF. All the graphics you saw that was done with Windows Presentation Foundation, I really like it a lot. It has retained graphics, which is kind of like the GC for graphics. You don't have to do a lot of your eventing. It's taken care of for you by the retained graphics system itself. That's kind of cool. I like Scheme for embedded languages. I think it has a lot to offer for that. So looking ahead, to me, I think it's a clear case of functional programming is the way of the future, and monads are the biggest advent to make that happen. As George Santayana said, those who can't remember the past are condemned to repeat it. As some addendums, I wish F# had type classes. There's some discussion about that. I don't think F# will ever get type classes, and I think the reason why is the type system in F# is very ML-like. It's very Haskell-like, except that it's a lot simpler, so that makes it more accessible to .NET programmers that are used to C# and imperative languages. And I think the fear is that it's too late in the game to add a more sophisticated type system, but maybe that will happen with some other language that will supplant F# and do it using what was learned from F#. I like Haskell, and I noticed that Haskell is becoming more impure. I mean, there's monads for mutation. Even Haskell has arrays that will let you do mutation. Another observation is the web is just completely taken over in a way I hadn't anticipated it would. Even desktop publishing, desktop graphics and systems are all done using web technologies. I really don't like web technologies because they're lowest common denominator and they're very ad hoc, but because of their ubiquity, they've kind of taken over. Resistance is futile. And finally, if we look further into the future, what will be, I think Alan Kay has the best admonition on that. He says the best way to predict the future is to invent it, and I couldn't agree with that more. We shouldn't be wondering what the future is going to hold as if it's some static thing that arrives and drops in our lap. It's up to us to make it and make it be whatever we want. And that's the end of my slideshow. Any questions or comments? While you're thinking about that, I did want to put a plug in. I am going to have a talk tomorrow at 4:30 called Type Providers Making Data First Class. Type providers were invented in F#. They also have them in Idris, but from what I'm told, they're very different in Idris. Haskell's trying to get them, but when I look at the Haskell projects for having type providers in Haskell, they look like they're more wish list items right now. It's very seminal, but I applaud them for trying to implement them in Haskell. But anyway, I'll be talking about type providers at 4:30 tomorrow, and type providers just as in a nutshell, if you haven't heard about them before. Essentially, you give a live database connection or a live connection to some data source, and at the IDE time, it runs in, makes a schema for you, makes erasive types for you, and lets you explore your data source through the IDE in IntelliSense in the IDE, and gives you a type inference and all kinds of things that we really like for doing development. So I highly recommend, if you're interested in database programming and don't like worms, that you might want to take a look at that talk tomorrow. Any questions? All right, that's it. Thanks.